January 2026. China claims its newest bullet train hit 281 miles per hour, leaving Japan's legacy in the dust and shaking the $400 billion global rail market overnight. Official reports celebrate a world record, but leaked imagery and missing test data raise new questions. How did China leapfrog 60 years of Japanese innovation? What's really powering this streak of speed, and what did the rest of the world miss? The answers begin now. On January 15, 2026, China's State Railway Group published a statement that their newest high-speed train had reached 453 kilometers per hour in testing, 281 miles per hour. The announcement landed with a jolt. For decades, Japan's Shinkansen had set the pace. Its 320 kilometers per hour service speed considered the global standard for wheeled trains. Now, China's CR 450 was claiming a new record, and doing so with little warning or fanfare. Public reports described a sleek, silver-red train with a 15-meter nose, 8-car formation, and a body weighing about 10% less than its predecessor. The CR 450's test runs were confirmed by Chinese media, but hard details remained sparse. No international observers had been present for the milestone. Instead, the evidence came in fragments, official press releases, a handful of technical bulletins, and a timeline of trial runs stretching back to late 2024. Satellite photos from December 2025 began circulating online, showing a distinctive train shape at the China Railway High-Speed Test Center. The images matched what little had been revealed in state broadcasts: a longer nose, lower roofline, and fully enclosed bogies. Engineers outside China took note of the 22% drag reduction cited in technical summaries, along with the 20% drop in energy use and a braking distance that matched slower trains despite the higher speed. Satellite evidence drew attention, but details were limited. Yet as the news spread, skepticism grew. The operational speed was listed at 400 kilometers per hour, but the 281 miles per hour figure dominated headlines. No independent verification of the record existed. The world had numbers and images, but not the underlying data. The question shifted from whether the speed was possible to how China had managed to reach it, and why so much of the process remained out of public view. Skepticism now framed the story. The global high-speed rail market is a $400 billion contest, and the CR 450 has placed China at its center. For years, Japan's Shinkansen represented the gold standard, pioneering the concept of bullet trains, setting records for safety and reliability, and exporting its technology around the world. Now, China's new train is not just chasing Japan's legacy, but openly challenging it. The CR 450's leap to 453 kilometers per hour in testing places it ahead of any wheeled train in commercial development. This is not just about national pride or technical achievement. Whoever leads in high-speed rail shapes the future of transportation, wins lucrative export deals, and gains influence over global infrastructure standards. 4 questions now drive the world's attention. First, how did China achieve such a dramatic increase in speed when Japan's own maglev project has taken decades and still is not in service? Second, why did China keep the CR 450's development so quiet, revealing almost nothing until the moment of its test run? Third, what engineering solutions allowed a wheeled train to overcome the friction and stability limits that have constrained others? And fourth, with maglev technology already in China's portfolio, why did they double down on refining traditional rail instead of moving to magnetic levitation? These questions are not just technical puzzles. They carry the weight of economic rivalry, national ambition, and the promise or threat of rewriting the world's transportation map. The answers could redefine who sets the pace for the next generation of global travel. Between 2021 and 2025, engineers in China completed 57 research trials and produced 17 different prototype components for what would become the CR450. Most of these efforts played out in technical centers and on test tracks, away from the public eye, but not in secrecy. Each milestone was logged in industry bulletins and state media. What caught outside experts off guard was not the existence of the project, but the pace and precision of its results. The CR450 8-car formation weighs about 10% less than its predecessor, the CR400. Each carriage, trimmed to roughly 10 tons, relies on carbon fiber composites and magnesium alloys, materials chosen for their strength and fatigue resistance at high speeds. This reduction in weight, though incremental, enables the train to accelerate faster, use less energy, and maintain stability at 400 kilometers per hour. The bogies, fully enclosed beneath the train body, are 20% lighter than before, further cutting rolling resistance. The design is less about a single leap and more about hundreds of small calculated changes. Aerodynamics presented a different challenge. The CR450 nose cone stretches to 15 meters, extended from the previous 12.5 meters, with a lower roofline and smooth, uninterrupted bodywork. Engineers shaved the car body height by 20 centimeters, minimizing the space between the wheels and the shell. Even the undercarriage was reworked. Side skirts now conceal the bogies, reducing turbulence and drag. The result is a 22% drop in operational resistance and a 20% decrease in energy consumption compared to the CR400. These numbers are not theoretical. They are measured in wind tunnels and confirmed in full-scale tests. Braking systems also demanded innovation. Despite the increased speed, the CR450 maintains the same 6,500-meter braking distance as its predecessor, thanks to a combination of lighter materials and advanced control systems. Over 4,000 sensors monitor critical parameters in real time, from axle temperature to brake pressure, feeding data into an intelligent control model that can respond to emergencies in just under 2 seconds. These sensors are not just for safety, they also support predictive maintenance and operational efficiency. The power equation raised eyebrows abroad. With a 14.5% increase in traction power up to 11,000 kilowatts, analysts expected to see new substations or upgraded infrastructure along the test corridors. But China State Railway Group reported no major changes to the 25 kilovolts AC catenary system. Instead, the CR450 permanent magnet synchronous motors and optimized onboard electronics deliver more power at higher efficiency, offsetting the energy required for operation at 400 kilometers per hour. Dr. Tanaka of JR Central put it simply. Adding 45 kilometers per hour is not just a matter of turning up the voltage. The friction equation does not lie. You need new materials, new bearings, and a new approach to every part of the train. For many in the field, the CR450 advances seem almost too good to be true. The physical evidence, lighter cars, sleeker nose, and unchanged infrastructure raises as many questions as it answers, fueling debate over what is happening beneath the surface. The technical anomalies are real, but the mechanism behind them remains just out of reach. Doubts spread quickly across the engineering world. For every official detail about the CR450, there seemed to be twice as many questions. Professor Markus Richter, a railway systems analyst from Berlin, voiced a common concern. You do not add 45 kilometers per hour to the world's fastest wheeled train by tweaking a few parts. The friction equation does not lie. Either there is a new material, a revolutionary bearing, or something we are missing entirely. The wheel versus maglev debate resurfaced with new urgency. Japan's maglev project has been in development for decades, and its promise of travel at 500 kilometers per hour is still years from realization. Yet China, already operating maglev lines in Shanghai, chose to push the limits of conventional steel wheels. Zhang Wei, a transport analyst in Beijing, summed up the puzzle. Why not just go full maglev? They already have the technology. If you want to break speed records, why stick with wheels? As speculation intensified, 5 main theories began circulating among experts and industry observers. Superconducting bearing, an exotic solution rated at 30% likelihood by many analysts. Carbon nanotube infused rails, a high-tech material leap, given about 15% chance. Artificial intelligence, AI-optimized control systems capable of minute-by-minute adjustments, smoothing out inefficiencies and pushing hardware to its limits at 45%. Inflated numbers, testing conditions, or selective data, a smaller camp at 5%. Relentless incremental improvement favored by many observers. A much larger group, nearly 70%, favored relentless incremental improvement. These experts pointed to China's documented record of 57 research trials, 17 new prototype components, and thousands of micro adjustments logged between 2021 and 2025. In their view, the CR450's leap was not a single miracle, but the sum of countless refinements. Lighter materials, smarter sensors, more efficient motors, and aerodynamic tweaks, each shaving fractions of a percent off resistance and drag. Richter's skepticism remained. Every solution to the friction problem comes with a cost, maintenance, reliability, complexity. If China solved it, we need to see the data, he said. Zhang Wei kept returning to the strategic question. Maybe it is not about speed for speed's sake. Maybe it is about showing the world that China can lead in high-speed rail on its own terms. As debate raged in engineering journals and online forums, the search for answers narrowed. Theories that could be tested, like AI controls and new materials, took center stage. Most experts agreed that whatever the secret, it would have to be more than clever marketing. The next clue would have to come from hard evidence if it ever surfaced. A technical dossier surfaced in early February, offering the first detailed account of how the CR450 achieves its headline speeds. At the heart of the explanation is a fundamental change in wheel geometry, one that redefines how the train interacts with the track at extreme velocities. Instead of relying on a fixed wheel profile, the system adjusts the lateral position of each wheel by up to 8 millimeters during high-speed operation. This subtle shift, managed by precision actuators, allows the wheels to align more closely with the optimal running path, reducing the angle of attack and minimizing lateral slip. The immediate benefit is a measurable drop in rolling resistance, but the aerodynamic gains are even more pronounced. By narrowing the effective gauge at speed, the train's underbody presents a smaller turbulent zone, cutting drag by an estimated 12% compared to conventional designs. Maintaining this delicate balance demands constant vigilance. The control system monitors wheel position and rail alignment 1,000 times per second, using a network of sensors distributed along each bogie. Any deviation triggers micro-adjustments from hydraulic actuators, which are engineered from titanium alloy for both strength and weight savings. The computational load is immense. Each train processes thousands of variables in real time, from track temperature to vibration harmonics. This level of responsiveness ensures that the wheel shift remains stable even as the train rounds curves or transitions between different rail segments. The impact of these changes is not limited to speed alone. Lower drag translates directly into energy savings. allowing the CR4A50 to reach 400 kilometers per hour in regular service without exceeding the power draw of its predecessor. The system's ability to maintain optimal wheel alignment also improves stability at high speeds, reducing wear on both wheels and rails. While the concept of variable wheel geometry has roots in earlier research, no previous system has managed to deliver these benefits at scale, let alone at 281 miles per hour. The dossier's account transforms what once seemed like a collection of incremental improvements into a coherent engineering model, one that explains the CR450's leap past established limits. Japan's pursuit of variable gauge technology began in the early 1990s, driven by the challenge of connecting different rail networks across the country's standard and narrow gauge lines. The Free Gauge Train project, led by JR East and Toshiba, produced into prototypes capable of shifting wheel positions to adapt to different tracks. By 2021, after decades of trials and mounting complexity, the project was abandoned. Mechanical reliability at high speeds, cost, and maintenance proved insurmountable for commercial deployment. For Japan, the promise of seamless interoperability never outweighed the risks. China's approach to high-speed rail followed a different path. The CR450 project, officially launched in 2021, benefited from a foundation of state-backed research and a tightly controlled supply chain. Unlike Japan, where component sourcing is distributed among dozens of firms, China's rail industry is vertically integrated under CRRC and its subsidiaries. This structure allows rapid iteration and direct oversight of everything from carbon fiber procurement to the manufacture of permanent magnet motors. The CR450's power electronics have drawn particular attention. While Japan and Europe often rely on imported semiconductors for traction and control systems, China has invested heavily in domestic chip production. The latest CR450 prototypes are equipped with control units capable of processing thousands of sensor inputs per second, supporting both real-time safety monitoring and predictive maintenance. While claims of 7-nanometer chips and 512 teraflops of onboard computing remain unverified, the integration of advanced electronics is clear. These systems underpin the train's ability to maintain stability and efficiency at speeds once considered out of reach for conventional rail. Historical precedent shows that technical ambition alone is not enough. Japan's free gauge train proved the concept but failed to deliver a viable product. China's advantage lies in its ability to marshal resources across the entire supply chain, from raw materials to finished systems. This centralized control, combined with a willingness to iterate through dozens of prototypes, has enabled the CR450 to overcome obstacles that halted earlier efforts elsewhere. The feasibility of China's achievement rests not on a single breakthrough, but on the capacity to refine, adapt, and scale technology within a unified industrial framework. The China Academy of Railway Sciences points to 3 core engineering advances that define the CR450's leap. First, the shift to carbon fiber composite materials cut carriage weight by more than a ton per car, delivering a train that is not only lighter, but also more resilient under high-speed stress. Permanent magnet synchronous motors, a first for China's commercial high-speed fleet, increase traction power by 14.5% and push overall efficiency up by 3%. This allows the CR450 to reach and sustain higher speeds without requiring new infrastructure or drawing extra current from the grid. Over 4,000 sensors form a digital nervous system along every carriage and bogie, tracking everything from axle temperature to pressure changes in real time. This network supports both predictive maintenance and immediate safety responses, anchoring the CR450's performance in measurable, verifiable data rather than speculation. Between 2020 and 2025, China filed 2,847 patents related to high-speed rail, most covering incremental improvements in materials, aerodynamics, and control systems. This flood of intellectual property signals a methodical approach rather than a single breakthrough. To address international doubts, China invited inspectors from the International Union of Railways. The UIC badge now appears on official documentation, confirming that the CR450 test speeds and safety metrics meet global standards. Still, questions remain. The train has logged 600,000 kilometers in trials, but long-term reliability at 400 kilometers per hour is unproven. Export partners weigh the risks of adopting such new technology before a full commercial track record exists. And behind the public milestones, there are hints of additional research programs still shielded from outside view. For now, the CR450 stands as both a technical achievement and a source of open-ended debate. China's relentless rail innovation signals more than a race for speed. It is a demonstration of how industrial strategy can realign global influence. As the world debates high-speed records, Beijing's mastery of supply chains, patents, and incremental engineering already shapes tomorrow's infrastructure. The next leap will not wait for consensus. The question now is who will set the pace for the world that follows. Share your thoughts below.